All right, good afternoon, everyone. Yes, I'm in that the slump of the afternoon talk, always the popular one. All right, my name's Angus, or Gus. I work for Bitnami. People either know a fair amount about Bitnami or they've never heard of them. So if you're in the never heard about them camp, we package up software and we make it available in a whole lot of different formats. Most people know us through our virtual machine images that you get from the Amazon Marketplace, for example. I'm on the Kubernetes team in Bitnami, and we are exploring how to ship software for Kubernetes, how you package up software, how you configure that. And we've done a bunch of tools like Kubeless. It's a functions as a service framework. Sealed secrets. It's a way of encrypting your secrets outside for the part of the workflow where they're outside the cluster. And what's some other things? Kubeapps, which is a Helm marketplace for Helm charts. And one of the things we do a lot is the Helm. We're very involved in Helm, and we do the stable charts for Helm. Most of the stable charts, or a lot of the stable charts, are maintained by Bitnami employees. So that's a bit about Bitnami. Today, I'm going to be talking about kubecfg, but really, what I like to do in these sorts of talks is kind of step back and reflect. So what I really want to talk about is, why are we here? Why is Docker different? Why was it different to what we had before? Why was Kubernetes different to what we had before? And if you are new into this community, which some of the people here are, it's easy to miss all of that, because you just see the technology and you don't see the rationale and the path and the thought that went into building that tool. And so it's easy to bring in the practices you had before and use them with the new tool, and then you haven't gained the benefits. Really, you should be taking on the new practices as well. So that's kind of what I'm going to talk about today. So, context. In the beginning, we had physical computers. They were real, they were there. So the way you administered them was like this. You installed your operating system, then you logged in, and you installed packages, you modified files, you commented out lines from configs, you appended other lines to configs, and you could automate that using something like CF Engine way back, or SSH things, or Ansible, or any of those tools. But fundamentally, you were logging in and you were modifying the machine. And each of the processes to do this were separate. So you had one process for installing. I'm going to install my Debian distro this way. You had a process for upgrading from version of my software last week to the version of the software this week, where you logged in and you installed some new packages or you copied in some new files. And then if ever you wanted to downgrade, you had a whole separate process for that too. You had to log in and restore a database backup or something like that. Usually downgrading kind of got forgotten about because it was hard and you pretty much never used it. Then along came Amazon in particular, and virtual machines became very popular. So initially, everyone was managing these in the same way. They would create the virtual machine, they would SSH in, they would install packages, they would modify it, they would append files, the same sorts of things. And that works fine. But slowly, people started to realize that these were virtual machines. I didn't have to modify them incrementally because I could create and destroy them for free. They're not real hardware. And so a whole new way of managing these machines came in, where you would, if you wanted to upgrade a machine, you wouldn't log in and upgrade it. Instead, what you would do is use your install process. You would pretend like you were installing a whole new machine. You create a new virtual machine. You'd install version N+1 onto that new machine. And then when you were happy with that, you would then destroy the old machine. So you'd done an upgrade using your install process. And this is kind of interesting, because now suddenly we could do all of these operations just using my install process. So I didn't have to have a separate process for upgrade. I didn't have to have a separate process for downgrade. Everything looked like an install. I just create a whole new machine from scratch, install into it, delete the old machine. And this is a big deal, right? We can do I can do a massive upgrade from a system running on Red Hat to a system running on Debian with an entirely different file system, an entirely different version of my software stack. And it looks the same as a regular update from minor patch version 7 to minor patch version 8, because it's still exactly the same process. Might be more risk, you might want to assess it a bit more before you continue the upgrade, but the process and the tools look the same. This went under a few different names. Immutable Images was kind of one of the buzzwords thrown around at the time, and you saw tools like Packer was a popular tool for building those images, but lots of other ways of doing it. So just looking at this process more, we ended up with kind of two ways of doing things. You could either do what we call the imperative method, where you're starting with some known starting point, and then you're making changes. Okay, you're logging in, you're installing a package, you're removing a file, you're modifying a config file. Or you have what we call a declarative approach, where you're not thinking about the changes so much, but you're looking at the snapshot of what the system's going to look like at each point. And you're basically replacing the system with the next version. And as I hope you can sort of see from this diagram, they're equally expressive. You can describe the same result. I can describe B equally well using either of those two approaches. But there's a number of differences in practice. In particular, the imperative approach relies on knowing that initial step. You need to know what A is. If I just do that change and that change and that change, and I started from a subtly different initial condition, I'm going to end up with a different result. Unlike the declarative, where I really don't care what came before. I could do A, then B, then D, and then I install C, and I've still ended up with exactly C. So in practice, there's actually some very important differences between these two approaches. People get really excited about this, and they start to bucket tools into one or the other. Puppet is a declarative tool. Ansible is an imperative tool. Like, I don't care. In particular, what I'd like to get across here is that the real world has side effects. The real world is stateful. So if you have some declarative tool, that's nice. At the bottom, there's an imperative tool that's actually doing the work. Okay, so you can't get all high and mighty and say declarative's awesome, we should just never do imperative, because at some point you need to make changes, and those changes have side effects and they have time involved. They're not an atomic transition. So in practice, you need to mix these two tools and these two approaches. The Docker file is a wonderful example. The Docker file is clearly imperative. It's clearly step, 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 step as you're running down the Docker file, building a Docker image. But it's actually reasonable to use because it starts from a very well-known starting point, that from statement. And at the end of it, you've captured the result, and you now have a blob that you can ship out and install and switch from blob version X to blob version Y, and you know the results that you're getting. So you've got the Docker file as this small imperative building block that you've used to build a declarative result and a declarative workflow around it. So we need to mix these two ideas. We can't just say that we're only in one camp and only in the other camp. But something, I know we talked about gitops in Gabe's keynote this morning. The declarative workflow is very powerful because it lets you talk about the change before the change has happened. As Gabe was saying this morning, you can have the state of your infrastructure declared in some config file in its entirety, and you don't need to care about what came before. You're just saying, this is what we're trying to build. And you can talk about that in the abstract. You can have a pull request. I'm proposing we build this infrastructure. And it doesn't matter what was there before. You can argue about it. You can change it. You can ignore the order that commits went in before, because when that one is merged, that becomes a statement of truth. For me, I was an SRE at Google for a very long time. I take the engineering part of SRE very seriously. For me, one of the big things about this is that it gives you a bounded time on disaster recovery. So when you do an upgrade, everything's wonderful and happy. You're rolling out some new version of your software. You roll out the next version, and then halfway through, there's a problem. When you're using the imperative workflow, the only thing you've ever tested is upgrades. Remember how there were different processes, install, upgrade, downgrade, with different processes under that workflow. The only thing you've ever really exercised is upgrades, because that's what you do every week. So when a disaster happens, when that upgrade fails, you're nervous. I'm in a place I don't know what to do. The only thing I know, the only thing I'm comfortable doing is continuing the upgrade. So you end up with heroes. You end up having admins who go, oh, I was up till 3 a.m. making sure the database upgrade that failed halfway through because the disk died and I had to replace the disk and then recopy that and then do that and that. And then, but it's okay because when I'd finished after many, many hours, it was all good and I got it back before everyone came into work on Monday. That's the imperative troubleshooting process. The declarative one, on the other hand, says, I've got an entire snapshot of the system, description of the system. I went to move to a new version of the system, and something went wrong, some unexpected issue. The safest thing I know how to do is reinstall the old version, because everything I do is an install. I can go from any initial starting point and just delete it and install the previous version. And I know how to do that because that's what I do every week. That's my upgrade process. And I also know how long that takes because I do that every time. So I know that from pretty much any failed point along an upgrade, I can revert and reinstall the previous version with a bounded time. I don't have to, there's no intuition, there's no creativity, there's no heroic troubleshooting. It's just, revert the git change, reinstall the previous version. So everything I do now has a bounded recovery time. And that's a big deal when you're scheduling changes and managing changes from that, higher level engineering point of view. So some people started doing this with VMs, but then along came Docker. In Docker, everything is like this. In Docker, everything is an immutable throwaway image. So everything looks like this. Throw away whatever you had and replace it with this. So when I saw Docker, what really got me excited was this was the first tool I'd seen that really made everybody think about this declarative workflow and made it easy to use and really commoditized it. And for me, that was very exciting. That was the reason I really liked Docker early on. And of course, you remember the early conversations. People wanted to run SSH inside their Docker images. Oh, I want to SSH in and modify my Docker image, and everyone else is going, no! Right? That's people coming in and seeing the tool, but not seeing the reason why the tool is there. All right, so then along comes Kubernetes. And Kubernetes, definitely no accident. Declarative everywhere. It uses Docker images. You declare what software is going to run. You don't say, first install this, then make that change, then make that change, then make that change. No, you just say, like this. We also have declarative configs. You say, my cluster, my manifest should look like this. I don't care what was there before. This is what it should be now. So every change you make, again, we don't have separate install and upgrade. Every change you make looks like declare, wait a little while for the machines to catch up, because underneath, of course, Kubernetes is an imperative process. It's actually making those changes, those side effects. And then eventually it's all running. Okay, so this is no accident. This is built on Google's experience managing large-scale infrastructure, building practices that would minimize configuration drift between machines, and how you come up with a stable system that's easy to maintain with a large group of people and a mature change process. All right, so to do this, we have kubectl. Everyone knows this tool. It's wonderful, it's great. It's basically a command line wrapper to everything you can possibly do with Kubernetes. Almost all of those are imperative commands. They do this thing, see the result. Only one of them is really a make it like this command, and that's kubectl apply. So everyone presumably is familiar with this. You build a workflow around kubectl apply. You have your configs in YAML or JSON, and you would have an integration step, which would be just kubectl apply -f your YAML files. It's pretty good, it works. You can certainly use this. It has a few limitations. In particular, it only reads JSON and YAML. It has a garbage collection. So I'll come back to that later, garbage collection. But it has a prune feature, which is limited in its implementation. It only works on a single namespace and only for some resource types. And it's a bit scary. You read it in documentation, it's full of warnings about this is alpha, be very careful, you know what you're doing before you enable it. So when I started to use Kubernetes a long time ago now, I wanted a slightly better tool for managing my configs. So we at Bitnami wrote this little tool called kubecfg. It's a small tool. It's definitely not a thing that we're putting staking the company on. But I think it's interesting, and I think people can benefit from seeing it and thinking about the rationale as to why this tool exists. This is a bit different. This tool is built assuming that declarative workflow. So it really only has two operations down the bottom there. It has the read-only version. It's like a lint tool. Is this config good? From what you can tell as a static analysis. And you would run that as a unit test. You run that all the time from the local developer testing and from your pull request CI test. And then it has an update command. And that's that apply, that's that push command. So that is get the configs and make it like this. There is no install command. There is a delete command, but there really shouldn't be. It's just always make it like this. Now, it's unashamedly inspired by the Borg CFG tool from inside Google. If you're in Google, you know what that is. And that people in Google love and hate this tool. It's a tool you use every day if you're an SRE, so there's a lot of feelings both ways about it. But we have an existence proof that this approach and this tool is capable of scaling to a company the size of, or a system, the complexity of about 10,000 engineers, about 10 years of evolution, about 100 data centers. That's a pretty good size, and we can say that this approach is capable of scaling to that. There's not many other tools you can say that about. Unlike kubectl, the encouraged use for kubecfg is to provide the whole config all in one go. So you don't give little individual YAML files. You say, here's my whole cluster, not the whole cluster, but the whole part of the cluster that you want to manage from this one CI/CD pipeline. And it's also a simple client-side tool. Unlike, say, Helm and with Tiller, this runs on the client side, so it fully obeys RBAC. It's just acting as the user that you're running the tool as. There's no in-cluster super user operator, so it's quite secure that way. And importantly, it can be used on multiple clusters, because for us, that was our use case from day one. So I can have one Git repository that can describe several different clusters, and I run kubecfg update against each of the clusters when I run when I merge into master. Whole config also allows me to sort the objects, so I know the full set of objects that I'm going to update. So kubecfg does a quick sorting of the objects to try to get them in a dependency order. And it also does garbage collection, which is like that prune feature, only this is reliable, and I have no qualms about recommending that you use it. Garbage collection is where you run an update, and then you remove an object from the config files, and then you run the update again. You want to notice that that object is gone, and you want to trigger it to be deleted on the cluster. The way this is implemented in kubecfg is quite different to the way prune does it. Kind of similar. Kubecfg walks all of the objects it can possibly find, looking for a tag. You put a tag on there, and it looks for objects with that same tag, and then compares that list against the list in the config. And if there's something there that wasn't in the config, it deletes it. So it's pretty simple, pretty robust. You can add an annotation to say, don't delete this because it's precious, I'm scared about it. So you can disable this on a per object level if you want to. All right, jsonnet. One of the interesting things is I support JSON and YAML and jsonnet. JSonnet is a small little language that came from someone from Google, but again, it's not an official Google project. It's a small mini language for generating JSON. That's what it does, nothing else. It's a real programming language. It's got rigorous definition behind it. It's Turing complete. If you wanted to, you can implement MD5 in it. It's just slow, but you could if you want to. It's a real programming language. The only thing it does is outputs JSON, or a string. It has no side effects. It's a functional language. It has objects. It has functions. It has quite complex things. On the right there, I've got an example. So the JSON at the top And then at the bottom, you can see the jsonnet equivalent of that. I don't need to quote keys if they're simple words, which is just slightly nicer syntax. I'm allowed to put trailing commas. I hate that about JSON. You have comments. And I have the ability to do some basic mathematics. So there I'm using self.chickens, which looks at the chickens value within that same object level and multiplies it by 2. Okay? So that describes the same JSON output. It's quite a nice language. You should go have a look at it. jsonnet.org has a better description of it. I use this everywhere I want to. So I use this to generate my Prometheus configs, which are now in YAML. So I just generate them with JSonnet in the same way. So I can do the same powerful templating and things operations. So yeah, it has templating. So here's another example of that. So here I'm importing that previous file. I'm now importing it from another file. So I can build collections from different libraries that I've got written by different people, perhaps. And then I'm overriding that farm object, and I'm setting the chickens value to be something else. Now, remember this one back here, self is lazy, self is late bound. So it's self.chickens is actually 5 here. So the drumsticks value is automatically recalculated to be 5 times 2, not the previous value. So you can see from this that I can build up quite powerful templates. I can build up libraries that are then shared and reused where some of the values are overridden, or perhaps I have functions with parameters and I'm generating different results, and I can compose these in quite powerful and complex ways to build large configuration. So there's been a few people who've written some Kubernetes template libraries. Ksonnet lib is an interesting one where they get the Kubernetes schema and generate functions, kind of a builder pattern style functions for all of those objects and all of those possible properties in each of the objects. Cube.libsonnet is that second one. That's the one I'm responsible for. It's a bit simpler. I think it's a little bit easier to use because it's got a bit more human involvement in how it was written in the first place. But it's also less comprehensive than the automatically generated ksonnet lib. And you could build any other library. There's no reason you have to use these two. You can use any other library you like. So what kubecfg basically does is reads in JSON or YAML or executes the JSonnet. And if it's executing, and then gets a bunch of objects and then pushes those objects to the cluster. If it's evaluating JSonnet, what it does is the result. So you can see the result here is whatever the last expression in your file is. It gets that object, and if it's a JavaScript object, it looks through the values. If it's an array, it looks through the items. So it tries to expand your JSonnet, looking for things that look like Kubernetes objects. So it looks for the kind and the API version fields. So this is really powerful because now you can have nested JSonnet. I can create a JSonnet file that includes nested objects, and kubecfg will just walk down it and find the kind of leaf objects that are described in there. And this is really important because you can import and mix and match now. So now your sharing primitive doesn't have to just be single resources. It can be collections of resources. I also add a bunch of other built-ins which aren't very interesting, and I allow you to import by URL, not just by file name, which is a bit easier when it comes to sharing. So here's a real example, if I can get, here we go. So here's a more realistic example. This is the classic guest book example from Kubernetes, except done using JSonnet. So the guest book example is a simple front-end PHP application with a Redis master and slave cluster. That's a pretty simple multi-tier setup. So here I could use this import by URL here if you wanted to. I'm just using the local import so that I can test this without needing the Wi-Fi. That imports the library. This is declaring a function called Redis, takes an argument called name, and this returns an object with 2 Kubernetes objects inside it, a service and a deployment. Now notice here, because I'm doing the whole config again, I can do a lot of cross-object referral. So here I'm referring to a value inside the deployment object. Dollar just means go back to the result of the current expression, so it's a way of going back to the top level and then walking back down again. So deploy spec template means here in the hierarchy. And then there's my deployment. Deployment looks very familiar. And so in my kube.libsonnet, I'm adding a few helper properties, which I just by convention chose to put an underscore afterwards. So in my library, I have an env underscore, and then I calculate env from that env underscore value, which just allows you to write a more simple key value object here, rather than the actual Kubernetes env structure, which is a list of name colon value colon, which is just a bit more annoying to type. But if you want to, you can override and just set an env directly here. So that's a function that gives you a Redis service and deployment. And then down here, I've got my actual result. And I have the front end, which is that service. And you can see here I'm merging in, I'm overriding the spec type. And here I've got the deployment, that's the PHP front end. And I can do useful things here where like the liveness probe and the readiness probe are derived from each other, because there's a lot of common patterns inside Kubernetes objects. And then here I invoke the Redis function twice. The master needs no other changes. The slave needs me to override a few values. So you can see all the pluses there. I'm merging in those values. I'm not going to try to describe the full syntax of jsonnet here. You can just go and look at the website. But you can kind of intuitively see what's happening there. So this is a good example of a library, the Redis library, that someone could consume, and they can still jump in and tweak every single possible value. I haven't had to add parameters to the Redis library to support every single possible configuration option, but the consumer can still set any possible thing they might want to do. This is, for example, Helm does not do this. Helm, you have to put explicit parameters through. So when I want to do something like set a node affinity on a job, which the chart author didn't think about, I can't just do that. I have to download the whole Helm chart and modify the Helm chart to add the capability to set the node affinity. Whereas with this approach, you can always just merge in anything you like. So you have full power and flexibility. So that's the result. And just to show you what this looks like, here is, whoa, where am I? Okay, so kubecfg, I can do show, and that's that same file. And you can see it just dumps out a whole bunch of that's the YAML as you'd expect to see there, with the various templates expanded. I can do kubectl get pods. Look, nothing up my sleeve. This is just minikube locally here. Kubecfg, update, guest book. Done. So that's run through a quick little validation there. I should have showed you validate. It's done the same thing as validate. Validate just expands the JSONet, that compares it against the schema. It does a schema of validation to make sure all the keys or values make sense. And then it's push it to the cluster. So if I now do get pods, I'm now running that infrastructure. Okay, so it's very simple, just what you see. And I can do things like, where's that guest book? And I can do something like change my image here to be a different version. And then I can do diff, show me the differences between what's running on the cluster and what have I got here. Woohoo! It's got lots of server-side stat stuff. Oh, and Emacs doesn't like red. Okay, apparently. Let me do strategy equals subset. I think that's the, nope. Live demos for the win. Diff strategy. There we go. So that just shows me the differences. It ignores any value that only appears on the server. So things like the UIDs and things get ignored in the difference. So it's a much cleaner difference. And if I scroll up here, there's my diff showing that I've changed that image version. Okay, so it's pretty simple. The main commands, as I was saying, are just validate and update. Pretty much nothing else. That's most of my talk. Since we wrote this tool, Heptio, some of the guys at Heptio got excited about it, and so we've now put it into a joint project we call ksonnet. It's kind of jsonnet and Kubernetes. So we now have this project that involves Heptio and Bitnami and a bunch of other people, including the author of jsonnet himself, who's very active in our Slack channel. And so there's now the ksonnet/kubecfg tool, which is the one I've just talked about. There's also a newer tool, ksonnet/ksonnet, which Heptio guys have been talking about. You can see one of their talks from KubeCon, for example. And it's the similar ideas, but the command line interface is very different, and it's a much more opinionated tool. It's got, it wants you to have files laid out in this particular way, and it uses that layout to be able to do some more, to provide more value out of the box. Whereas with kubecfg, you kind of have to build it up yourself with your template libraries. If you want to ask any questions about this, there's quite a lively community on the ksonnet channel on Kubernetes Slack. And then down the bottom here, I've got a bunch of kind of secondary links. The ksonnet lib and kubelib-sonnet, which I pointed to earlier on. And there's also a blog post there, which I wrote quite a while ago now, about how we manage our clusters in Bitnami, which talks a lot more about the workflow and how we put it together and how we structure the templating. We have like a common layer of templating that is very just Kubernetes generic. And then we have a layer that is for each of the components. So Prometheus will have a file at that level. And then we have another level for each cluster. And each cluster will bring in the particular components. It'll customize them if needed for that particular cluster. And then be the config for that resulting cluster. So the cluster is always in control. You can change anything you like about each cluster because that's the top level of the file. And most of our configs, it's actually like literally a copy of our production configs minus a very small amount of stuff is available on that kube manifest if ever you want to go and look at what this would look like for a real production cluster. And that's what I've got. So thank you very much.